All right, welcome everyone. We're going to talk through a couple concepts from Chapter 3, and a lot of these are kind of like the application of moles and stoichiometry. So it's if you are going to apply moles and stoichiometry without kind of diving into any of the other chapters, these would be a couple of applications for it. So the first one is called combustion analysis or elemental analysis or empirical analysis, something like that. So here's what happens in this situation. Let's say you are a scientist and you find a rock sitting in a field and you want to know what it is. So what do chemists do when they're not sure what things are? Well, we burn them, of course, because we're chemists. Of course we burn stuff. Okay, so I'm not even kidding about this. They put it into what's called a combustion chamber, and you're going to burn your sample. And when you burn your sample, assuming that it's combustible, here's your little combustion chamber. Here's your little sample down here. Okay, so when you burn it, it's going to combine with oxygen, and then it's going to give off some gases. Now, if your thing that you're burning is a hydrocarbon, meaning that it's made out of carbon and hydrogen, you're going to get out carbon dioxide and water if it's a perfect clean burn. If it's not a perfect clean burn, you're also going to get out carbon monoxide and carbon soot, just like we talked about in our Bunsen burner lab last year in chemistry. So you're going to get out gases. Now, it might not always be these gases, but a lot of times these are the easiest ones to deal with. And so you're going to collect these gases in these chambers. So you can see like this one is filled with a water absorber, so you can figure out how much water you have produced. This one's filled with a carbon dioxide absorber, so you can figure out how much carbon dioxide you produced. Oxygen and other gases are going to be passed through. If you have other gases that are forming, you're going to have to collect those in another way. And what you get out of this combustion chamber is information. Now, the information we're going to use we're going to apply stoichiometry to these gases, and we're going to backtrack to see if we can figure out how much of our original thing we made. So we use our product and we calculate back to our reactant. So that's what this whole problem is about. The whole problem is about calculating back to your original compound, because we want to know what your original compound is. So what we're looking for is called your empirical formula. Now, if we know that your compound originally had carbon and hydrogen in it, then all you're actually looking for are the subscripts. And now here's where you think to yourself, what unit are those subscripts in? Are those subscripts mass? Are they volume? Are they moles? What are those things? And they're moles. These subscripts are always going to be measured in a counted amount. So we can say we have 1 carbon to every 4 hydrogens. That's a counted amount. 1 atom to 4 atoms, or 1 dozen to 4 dozen, or 1 mole to 4 moles. All of those are counted amounts. And since we're dealing with super, super large numbers of super, super small things like atoms, then the easiest way to count those large numbers is to count in moles. So what we are looking for is moles of carbon and moles of hydrogen. All right, so There's one more catch to this problem, and then we'll actually just go through an example, is the carbon to hydrogen is actually a ratio. And ratios are beautiful, beautiful things. I don't know if you've ever loved a ratio before, but I'll tell you what, start to love them because they save you so much work in chemistry. And this is one of those examples. So we are looking for the amount of moles of carbon to hydrogen, but we don't even need the exact amount of moles for an empirical formula. We just need the ratio. So if you tell me, if you can calculate to, let's say it's 1 carbon to 4 hydrogens, that's great. Or if you can calculate to 2 carbons to 8 hydrogens, that's fine too, because it's going to give us the same end result. Or let's say 10 carbons to 40 hydrogens. This is the beautiful thing about a ratio, is that all of these possibilities, let's even say 100 to 400, or like 2,000 to 8,000, all of these ratios down here are going to simplify back to our one ratio that we are looking for in our empirical formula. So your math can be a little bit less exact, or your math process can be a little bit less perfect, because you don't actually need to come up with the numbers 1 and 4. You just need to come up with that ratio, and we can simplify down to 1 to 4. So keep that in mind, that the whole way through this problem, we're dealing with a ratio. All right, so let's look at an actual combustion analysis problem. In this example here, we are given a little bit of information. So they want us to determine the empirical and molecular formulas. So we'll get there. And then the compound has been analyzed, and they give us the following mass percent. So 71 chlorine, 24 carbon, 4 hydrogen. And then they give us the molar mass also. Okay, so notice that they're giving you this information in mass percent, which means that this percent is not in terms of moles. It's in terms of mass. So we're going to start. Let me just set up this information. Okay, so we have not a whole lot of space here, but let's do our best. Let's go 71.65% chlorine, 24.27% carbon, and then 4.07% hydrogen. All right. Now, these are in percent by mass, which means that we can play with these as well. Again, ratios are going to be your favorite thing. So if I have 71%, I don't know how much my actual rock weighs. Maybe it weighs 2 grams. Maybe it weighs 2,000 grams. I don't really know. But I do know that out of every 100 grams of this sample, 71.65 grams of those are going to be chlorine. And so I can turn percent into mass by making that assumption. Let's pretend that this is a 100-gram sample. Okay, now it may be, it may not be, but all I care about in the end is the ratio of chlorine to carbon to hydrogen. So the actual mass doesn't matter, because all I really care about is that percent. So I can make an assumption that helps me mathematically as long as I don't break that ratio. So I'm going to say that for every 100 grams of the sample, 71.65 grams of those are chlorine, 24.27 grams of those are carbon, and then 4.07 grams of those are hydrogen. Now, I have my stuff in grams now. Look what we've done. We have gone from percent into grams, which is nice. I don't like dealing with percent. Percent makes me a little nervous, but grams I feel more comfortable with. It's still not what I want though, right? I want the empirical formula, and those subscripts in that empirical formula are measured in moles. So now what I need is I need to get them in moles. We can do that. We can do a conversion between mass and moles. So grams of chlorine to moles of chlorine is on the periodic table. That's going to be 35.45. All right, grams, oops, I did that opposite. Grams of carbon to moles of carbon. Shoot. All right, take that 35.45. Let's put that on the bottom because that's our amount in grams. 35.45 grams per 1 mole. Makes a little bit more sense. All right, 12.01 grams per 1 mole. Let's go hydrogen. Grams of hydrogen to moles of hydrogen. So that is 1.008. All right, and now we just have to do these calculations. Okay, 71.65 divided by 35.45. And I get 2.021 moles of chlorine. All right, 24.27 divided by 12.01. And I get 2.021 moles of carbon. And then 4.07 divided by 1.008. And I get 4.038 moles of hydrogen. Okay, now if you can do this without hitting the equal sign on your calculator, if you once you get like rolling in these problems, that's best. What you don't want to do as we get into calculations is you don't want to like do part of it equal sign, part of it equal sign, part of it equal sign, because every time you hit the equal sign, your calculator just rounds it off. So at any point in time, if you can use second answer instead of the equal sign, do it. Use second answer. Okay. That was a side note. So notice here I have converted. All I've done is I've gone from grams into moles. All right, so I am in moles. That's what I want to be in, but I don't want to type in decimals to my empirical formula. I don't want chlorine 2.02 down here. We can't have decimals as a subscript. So I need to now just manipulate my numbers. Now this is a math game here. I just need to get from decimals into a whole number. Again, you're dealing with a ratio, so it doesn't really matter if we change our numbers as long as we keep the ratio the same. So in other words, whatever we do to one number, we just have to do that consistently all the way through so that our ratio stays the same. So the easiest thing to do at this point in time is divide by the lowest or smallest number. So I'm going to divide them all by 2.021. And what that does is it gets at least one of them into a whole number. And in this case, it actually gets two of them into a whole number. Now this one down here, 4.038 divided by 2.021. 1.998 moles of hydrogen. So I still have a whole number or a decimal there to deal with. Now, when you get to this point in time, and only when you get to this point in time, only after you have done your due diligence of dividing by the lowest number, are you going to look to see if you can round this number off. At this point in time, all of your numbers here, all of your moles here should be close to a decimal. It's either going to be a whole number, it's going to be a fourth, a third, a half, I guess you could go like 2/3 and 3/4 also. So one of these decimals is probably very likely to where you're going to be. So you want to look at your decimals here and think, okay, what is that the closest to? Is it closest to a whole number? 0.25, 0.33, 0.5, 0.6667, 0.75. What is that closest to? And for us, it's closest to a whole number. And so we're going to now round this number for hydrogen into 2. If I had gotten something like 2.25, then you need to multiply all of your amounts, chlorine, carbon, and hydrogen, by something that will get you into a whole number. But in this case, we don't have to multiply. Now, do not round before this step. If you round off after you convert from grams to moles, you might get lucky and it might just work out for you, or you might totally like shoot yourself in the foot and it will not work out for you. So do not round until you have divided by the lowest number. So now that we have everything in whole numbers, we can do chlorine 1, carbon 1, hydrogen 2, and there you go. That is our empirical formula. We made it half of the way, not all the way yet. So we have found our empirical formula. We can pat ourselves on the back for that one. We still need to find the molecular formula. So remember, difference between empirical formula and molecular formula. Empirical formula is the lowest possible ratio, and that molecule that has the lowest possible ratio of atoms may or may not exist. In the case of something like water, that is an empirical formula. It's the lowest possible ratio of hydrogen to oxygen, and it also exists. Something like Ch2O, however, is the lowest possible ratio of carbon, hydrogen, and oxygen in glucose, but Ch2O isn't the molecule that actually exists. The molecule that actually exists is much, much bigger. So now we need to figure out what our molecular formula is. Okay, I'm going to erase this and we're going to move into molecular formula. Okay, so we have empirical formula and molecular formula. Now, it's helpful if we take into account what we have. We know the empirical formula, ClCH2. We just found that. We don't know our molecular formula. We do not know how much our empirical formula weighs, but we are given information about our molecular formula's weight, 98.96 grams per mole. Okay, so we need to figure out these two pieces of information. Now, the molecular formula itself is what we're going for. This is going to be our answer. So we need to look at our other piece of information that we need, which is molar mass of our empirical formula. And that we can find. That's a periodic table thing. So let's figure that out. 35.45 plus 12.01 plus 2 times 1.008. So this molecular formula here is 49.48 grams per mole. Now, we want to know these two things, molecular formula and empirical formula, they're always going to be a whole number ratio to each other. And so we just need to figure out what that whole number ratio is. Is the empirical formula, does it need to be doubled to get to the molecular formula, or tripled, or quadrupled? That's what we need to figure out. So you may be able to see it just by looking, or if you just divide the two, bigger by smaller, you're going to get your answer. So the molecular formula is twice as heavy as the empirical formula, which means we can just take our empirical formula and multiply it by 2, So Cl2, C2H4, and that's our molecular formula. So lots of steps here, lots of logic here. The good thing is that if you ever run against like a combustion analysis problem or an elemental analysis problem, it's all really similar. Usually they give you percents. If it's a percent by mass, you need to convert mass to moles. And then once you're in moles, you need to manipulate it so you get a whole number ratio. And then you compare empirical formula to molecular formula in order to find the answer there. So notice we're taking chemistry, we're applying math to it, and we're throwing in a healthy dose of logic. And that, my dear students, is what we call AP chemistry. It's chemistry plus applied math plus a whole lot of logic. So if you treat this kind of like a puzzle, if you go at it like, I don't know how to do this, I'm going to problem solve through it, I love a challenge, keep in mind that like failing is not a bad thing. If you fail forward is my new favorite term. Failing will help us learn where we need to change, what we need to learn. And we're going to do a lot of failing together in this class. And that's okay, because that's what scientists and engineers do, right? They try something, it fails, and they learn from it. They try something, it fails, and they learn from it. It's a really uncomfortable thing, especially when, your whole school life, you've been told that like a perfect score, a 4.0 is essential. You need it. It defines you. Well, here's news for you. You don't need it. It doesn't define you. You're a beautiful person with or without a 4.0. You have a whole lot to offer to the world. And one of the things I want you to learn this year is learn to be okay with failure, because it helps us learn so much more than success does. So try these things. When you come against these problems, try the problem, get stuck, and then ask the question where you're stuck. And you'll learn a whole lot about yourself and your mind and your brain and your processing and chemistry in the process of figuring out where you get stuck and asking a question from that point forward. And I promise you, we'll all get there together. If you just keep trying and you just keep asking questions, we will all get there together. Okay, so that's empirical molecular form from a combustion analysis. This slide just kind of steps you through the steps that we just talked about. Making that assumption of 100 grams is probably the easiest. And remember, the actual amount doesn't matter, because you're just interested in what the ratio is. Get yourself from mass to moles is this step 2. And then get yourself out of decimals into whole numbers is this step 3 and 4. These are the steps laid out for you to get yourself from empirical formula to molecular formula. Remember, the empirical formula is always and forever a multiple. The molecular formula is always a multiple of the empirical formula. It's never a strange decimal, because you can't have a quarter of an atom, right? You have to have either 1 atom or 2 or 3. You can't have half an atom. So you can't multiply empirical formula by anything but a whole number to get to molecular formula. Percent composition. Percent composition is used a whole lot in empirical formula and molecular formula problems. So just getting comfortable with percent composition, or a percent by mass, being able to go from percent by mass to an empirical formula or the opposite, is a really good skill to have. So anytime we have a percent, all percents are going to be a part of something over the whole thing times 100. That is what a percent is. So if I'm asking you for percent composition by mass of the elements in this compound, I'm always just going to do part of the compound over the whole compound. And then if I want percent instead of a decimal, I'm going to multiply it by 100. So let's figure out what the molar mass of that compound is. 3 oxygens, 1 nitrogen, 1 sodium. So I get 84.99 grams per mole. And then if I want percent by mass of sodium, I'm just going to do sodium. And I'm going to use second answer on my calculator so that I'm not asking it to divide or to round off before I actually hit my answer. And I'm going to get 27.05%. Okay, so you can go ahead and figure out the percent composition by mass of the nitrogen and the oxygen in this. All right, those are your answers. Nitrogen is 16.47%. Oxygen is 56.48%. Remember, if you are figuring out percent, they should all add up to 100. So when you get to the last one, you can, if you are confident in your first two numbers, you can subtract by 100, or you can figure out your third one and add them all up to 100 to just double check yourself. Okay, let me erase these. And these are examples that will take you forward and backward for the mass percent. We're going to do that one and the one before it when we get together in class. Also, there's one in your book. Ooh, actually, this is a good one too. So notice just one thing. We will do this together in class, but one thing I want you to notice is they tell you that your compound contains only carbon and hydrogen, but then the stuff that they give you is carbon dioxide and water. So they don't actually ever tell you how much carbon you have and how much hydrogen you have. So this is part of that logic game. Can you figure out what your percentage of carbon is, what your percentage of hydrogen is when you're only given carbon dioxide and water? So hopefully you tried the questions in your book. If this was one of the problems in your book that you had questions on or got stuck on, go back and visit that and see if you can get yourself to a stuck place where you can ask a question to get yourself out of it. And then we'll do this one together in class. And this one. And this one. Okay, so now we have, we are talking about reactions. We're circling back to reactions a little bit. All right, and we're going to do this because this kind of brings us to our second application of the stoichiometry. So let's talk through this real fast. Now would be a really good time to pause your video and see if you can fill out this table. How many molecules are present given this reaction? How much mass? What's your amount in moles? What's your amount in mass in terms of grams? So I'm going to do it here also. I have 2 molecules of hydrogen, 1 molecule of oxygen, and 2 molecules of water. So molecules can be read from the coefficients. Mass in AMU, I would have 2 hydrogens, 1.008 times 2. So my molecule of hydrogen connected to hydrogen, is going to weigh 2.016 AMU. And then I have 2 of those. So I actually have 4.023 AMUs of hydrogen. I have 32 AMUs of oxygen. And I have 1 molecule of water weighs 18 AMUs. I have 2 molecules of water, so that's going to weigh 36.03 based on how many sig figs I kept off the periodic table. Oh, I guess I could have kept that. Okay. Amount in moles. So again, moles is going to come straight from those coefficients. I have 2 moles of hydrogen, 1 moles of oxygen, 2 moles of water. And then mass in AMU is going, or mass in grams, 4.023, 32, and 36.03. So take a minute and look at this table and think, what do you notice? What stands out to you? What's surprising? What's an aha moment? And hopefully what you see is your molecules and moles are really consistent. Also, your mass and your mass in AMU and mass in grams is really consistent too. And that's just because they're scaled up models of each other. If you take molecules and you multiply by 6.02 times 10 to the 23rd, you get moles. If you take mass and you scale it up according to the the conversion factor that I showed you earlier, you're going to see that mass in grams and mass in AMUs, they're just scaled up versions of each other. So you can read this equation however you want to read it, whether it's on an individual level, or on a bulk level. So using this information, knowing that we can interpret the reaction either on a discrete or individual level, or we can read this reaction on a bulk level using bulk quantities like a mole, we can look at this equation and kind of evaluate the equation a little bit. So let's see if this is on the next slide. If it's not, we can come back to this. Yeah, okay, so this would be a good example of it. If we look at the equation that they give us, it talks about, they give us a strip of zinc metal. It has a mass of 2 grams. It's placed in a solution with 2.5 grams of silver nitrate, and it causes this reaction to occur right here. Okay, so this would be a limiting reactant kind of problem. Basically, what they want you to do on these problems is go through the stoichiometry, but know what the stoichiometry means. So we are going to delve into the math behind chemistry now, but the catch is whenever you apply math, you must know what your answers mean. You can't just blindly calculate and chug out an answer and box it on your paper, right? So let's evaluate this a little bit. They tell us starting amounts, right? So they tell us we have 2 grams of zinc and we have 2.5 grams of silver nitrate. So these amounts are what's actually in my beaker. If I am doing an experiment in the lab, these are amounts that I have weighed out, and they are sitting in a bowl, in a beaker, in a graduated cylinder on my desk. So these are amounts that I call actual. This is what I actually have. Now we can calculate from these amounts 2 theoretical amounts. Now the theoretical amounts may or may not be like actually in existence. So let's look at a couple of these theoretical amounts before we try to answer these questions A, B, C, D below. So for example, I can take my amount of zinc and I can calculate to 3 different things. I can calculate to silver nitrate. I can calculate to silver, or I can calculate to zinc nitrate. Okay, so all of these are going to be the same. I'm going to have to get from grams of zinc, 2 grams of zinc. I'll show you one. I'm going to have to get out of grams of zinc into moles of zinc. Then I'm going to have to get from moles of zinc into moles of something else, like, let's say, silver. And then I can either keep it in moles if the answer doesn't specify what unit I need to use, like A. A just asks me which reactant is limiting. They don't say according to your calculations in moles or according to your calculations in grams. So I can do that one in any unit I want to do. But B, they say how many grams of silver will form. Well, I have to do that one in grams. And so if that's the case, then I need to go a step further and go moles of silver to grams of silver. So all of these calculations are going to look very similar. We're following ourselves through the mole hole. And in this case, we're starting in 2 grams of zinc. Now, whatever we calculate to grams of silver, in the case of my example above, or grams of silver nitrate or grams of zinc nitrate, those are theoretical amounts, and you need to be able to tell me what that theoretical amount means. So for example, in this calculation I have at the very top of the slide, I would be calculating the amount of silver that I could produce if all the zinc reacted. Right? It's a theoretical amount because I don't know if all my zinc is going to react or not. It might not. So I have an amount of product I can make if all my zinc reacts. Same thing with zinc nitrate. The answer that I get there is going to be the amount of zinc nitrate I can form, I can make, I can produce if all my zinc reacts, which that clause makes it theoretical. When I calculate to the amount of silver nitrate, what would that one mean? This would be a good time to pause and think about it. And if I calculate from 2 grams of zinc into grams of silver nitrate, it would be the amount of silver nitrate I would need if all my zinc reacted. Now, do I have that much silver nitrate? I don't know. I'd have to do a calculation to figure that out. But I could calculate how much silver nitrate I would actually need and then compare them. You could do similar calculations with silver nitrate. You could calculate from silver nitrate to zinc, the amount of zinc you would need if all your silver nitrate reacted. You could calculate from silver nitrate into silver. How much silver would you produce if all of your silver nitrate reacted? And then you could do the same thing for zinc nitrate. So from our 2 given pieces of information, we can calculate to 6 different theoretical amounts. You just have to be able to put into a sentence what that amount means. That's really, really important. Okay, so now to figure out what reactant is limiting, you can do this a bunch of different ways. You can calculate from amount of zinc you have into silver nitrate and compare the answers. You could go the opposite way, go from silver nitrate into zinc, compare what you calculate to what you actually have. But the way that I like to do it is I like to take both of my reactants and calculate to one product. And the reason I like to do it this way is because conceptually it's a lot easier for me to deal with that answer. And when I'm under stress, like in a testing environment, I need to know myself and know my limits and know what I'm going to be more likely to conceptualize correctly. So I know it's an easier setup. So I'm going to go from grams of zinc into grams of silver. I'm also going to go from grams of silver nitrate into grams of silver. Same thing. So I'm going to go grams of AgNO3, moles AgNO3. I'm going to go moles of AgNO3, which I'm just going to use for brackets, into moles of Ag. And then I'm going to go moles of Ag to grams of Ag. Okay, there's a second reason I'm going to do this. Not only for me is it conceptually easier, but in B, they ask you how many grams of silver you're going to form anyway. So if you set it up this way, you will have A and B answered without having to do more math. All right, so let's plug numbers in here real fast. So let's see here, 2 grams of silver to 2 moles of silver, 1 mole of zinc, 2 moles of silver to 2 moles of AgNO3. I know moles, and moles. Those are all going to be 1. And then mass of silver and mass of zinc. Okay, so zinc is 6539. Silver is 10787. Okay, and then silver nitrate 10787 plus nitrogen plus 3 oxygens, 16987. All right, so now I can do my calculations. On the zinc one, I'm going to go 2 times 10787 divided by 6539. So in this top one, from zinc, I can, if I react all my zinc, I can produce 12.19 grams of silver. All right, now for silver nitrate, 2.5 times 2 times 107.87 divided by 2 and divided by 169.87. Okay, and from silver nitrate, if all of my silver nitrate reacts, I can produce 1.59 grams of silver. So we can use this information to answer A. Which reactant is limiting? Well, the one that runs out first is going to produce less silver. And so that one is going to be silver nitrate. Silver nitrate's going to run out when we have only produced 1.59 grams of silver. Can zinc make more? Yeah, it can, but not without silver nitrate. How many grams of silver will form? Well, 1.59 grams of silver will form. Thank you so much for asking. All right, C and D. So C is going to be similar to B, only instead of calculating to silver, you're going to calculate to zinc nitrate. I'll let you try that one on your own. And then how many grams of the excess reactant will be left at the end of the reaction? So here's the deal. The excess reactant is going to be zinc. Zinc is going to be left over when silver nitrate runs out. And to calculate excess, you're going to take whatever you start with minus what you use, and that's what's left over. So we know what we start with. We start with 2 grams of zinc, but we don't know how much zinc we use because we haven't calculated that. So you can calculate that a bunch of ways. You can say, well, if I produce 1.59 grams of silver, how much zinc will I use? So you can go from silver to zinc, or you can go from silver nitrate. If I react this much silver nitrate, how much zinc will I use? I prefer going from silver nitrate because that's an amount I'm given. That amount is not something I calculated. And so I know that there's no errors in that number. There is a small possibility there's going to be an error in the amount of silver because I calculated it. So it's just a little bit safer to go with the given numbers. So that's what I'm going to do. Moles of AgNO3 to moles of zinc. Moles of zinc, and we need grams of zinc because our starting amount is in grams. So 1 mole, 1 mole. This is 1 to 2. And then we already calculated silver nitrate is 169.87 and zinc is 65.39. Okay, let's do this real fast. So 2.5 times 65.39 divided by 169.87. Also divided by 2. Okay, so I'm going to use 0.48 grams of zinc. And 2 minus second answer is 1.52. So 1.52 grams of zinc is going to be left over when silver nitrate runs out. Okay, again, just math, right? Not a whole lot of chemistry until they start asking you questions like A, B, C, and D. And then you really need to be able to tell me what your numbers mean. So this is really good practice to wrap your brain around what is molar mass? What is a mole ratio? What is a starting amount? What is an ending amount? Can I actually make this, or will something else run out before I can do that? So it's also a very beautiful, colorful slide. So look at us go. Double bonus. All right, we'll try some of these in class too. So good work today. Nice to spend a little bit of time virtually with you. Love you all so much, and I will see you in class.